Okay, in this video we're going to look at relativistic mass. So rest mass is like your mass when you're just sitting still, and then relativistic mass is going to be your mass when you're moving really, really fast, approaching the speed of light. So I'm going to start by giving you the equation, and just like before, you can kind of just scribble it someplace on this page, but I'm going to write on a separate sheet of paper just so I can try to keep my notes a little bit clearer. Alright, so here's the equation for relativistic mass. This is going to be the mass as viewed from Earth. This is going to be what's called the rest mass, or the mass of the person who's in the spaceship. And then on the bottom is going to be 1 minus v squared over c squared. Honestly, it's the exact same equation as the time dilation equation, just the t's are replaced with m's. So let's jot a few things down here real quick. This is going to be the velocity of the spaceship. Velocity of spaceship. This is going to be the mass on the spaceship. And this is going to be the mass viewed from Earth. Okay, so there's one new change we're introducing in this example, and that is the velocity. So if you're traveling really, really fast, and relativity only occurs when you are approaching the speed of light, it's very common to report velocities as a percentage of the speed of light. So we'll just pick an example here. So let's pick my example of 0.95 c. So the question is, how fast am I traveling if I'm going 0.95 c? 0.95 c means I'm traveling 95% of the speed of light. So to find my velocity, I'm going to have to take 95%, which is 0.95, times c, which is 3 times 10 to the 8th, and I'm going to number crunch that. So that would be 0.95 times 3e8. I'd be going that fast. That is going to be 2.85 times 10 to the 8th. So I'm going to write that down. I am going 2.85 times 10 to the 8th. So yesterday when we were doing the time dilation chart, I gave you the velocities in the true measures. But again, it's more common to report that velocity as a percentage of the speed of light. So you're going to have to convert those to the real velocity. We'll just totally skip this miles per hour because we are going super, super, super fast for those. Alright, so we now need to put somebody or something into the spaceship. And so my spaceship here, I have a rocket ship going down here. So instead of putting a person in the spaceship and sending a person out in space, I decided to use a bug. That's why there's this bug guy here. Alright, so we're going to put him into the spaceship. So I'm going to draw a little bug, and I'll put some little legs on him, and there he is in the spaceship. So because he's a bug, he's not super massive. So let's just pretend that he has a mass of 1 kilogram. Honestly, a 1 kilogram bug would be the biggest bug you've ever seen, but that'll make easy numbers here. So we can kind of put a 1 all the way down this list. So the question is, if we are in the spaceship going 2.85 times, or the bug is going 2.85 times 10 to the 8th meters per second, and he has a mass of 1 kilogram, what do we think the bug's mass is? So I'm just going to number crunch that over here. So I'm going to use my equation, and I'm going to start with, alright, this is how fast I'm going. That's my v squared. I got to square it. So squared. There's my v squared. Now I'm going to divide by 3e8 squared. 1 minus that answer. Then I have to square root that answer. And m0 is going to be the mass of the bug on the spaceship, which is 1. So 1 divided by that answer. And what do I see from Earth? He appears to have a mass of 3.2. He appears to have a mass of 3.2. So, in short, mass increases. When you go super, super fast, your mass will increase. Honestly, if you're walking down the street, your mass increases. If you're flying in an airplane, your mass increases. Not significantly, okay, like 1.0000000 whatever, okay, not significantly, but when I start to go 10%, 0.991% of the speed of light, my mass is going to start to increase fairly quickly. All right, so I'm just going to ask you to pick 5 more, so I'll say plus 4 more. That'll give you 5. Pick any 5 that you want. Make sure that this is one of the ones that you pick. And then number crunch and fill in the data just so that you can feel confident with using that equation. But let's talk now about some of the implications of this. So when we look at this bug, like when I say that his mass increases, I don't mean to say that like he blew up like a balloon. He stays the same size, well, at least for our discussion today. But his mass increases, so I'm just going to color him in. So he becomes more dense. Like he's the same size, but he becomes more dense. And actually, we're going to learn in the next lesson, he doesn't stay the same size. But the mass just increases the density of him. All right, the other thing I want to point out is it's very common in this relativity story to picture ourselves on the earth. And so I'll draw our standing here on the earth. And we like to picture ourselves having a velocity of 0. Kind of like I'm just standing here and I am watching this rocket ship whoosh on by. And he's got a big velocity. He's going 0.95 c. And we like to think that we're like normal. And that bug is getting really, really, really massive. Because this is our perspective. This is our frame of reference. But let's switch it around for a minute. What about this? By the way, we are not going 0. We technically are whizzing through the air. We just like to think of ourselves going 0. But this bug guy, this bug might think that he is at rest. He might think that he is at rest, and he looks at us and says, oh my God, look at that person. Look how massive they are. So this bug could look at us and pretend, I'm going to make this little fire rocket, okay, little fire coming off the earth here. Like we could look like we are riding a spaceship and he's at rest. So this is a cyclical story here. We like to think that our vantage point is the right one, and he, because he's moving so fast, is getting massive. But I could flip it. He could be looking at us and saying, oh my God, they look so massive. But within our own reference frames, we are the same mass, and the bug is the same mass. All you need to take away from this is when something goes super, super, super fast, its mass is going to increase. Today when we were talking about it in class, third hour was struggling a little bit because they really wanted to understand it. And I finally said, you're not going to understand it. Honestly, I don't understand it. Okay, I think it's kind of cool to talk about, but I don't understand it. I can't explain it sometimes very, very well. We're not Einstein, but we can just understand his takeaways from this. All right, I'll stop this video.